So next up, we're going to look at B here. Want to find the indicated partial derivatives there. Okay, so how would we do this? In the first part, they want us to get partial f, partial x, partial f, partial y. Then we've got that confused one where they're saying partial. That's going to be a confused one. Partial x, then partial z. Then there's that square there. Okay, so going to be interesting how we interpret that part there. And let's see what we're going to come up with. Okay, so the first one is straightforward. This, of course, is a function of a number of variables. We've got 3 variables there. First part, partial f, partial y, straightforward again. Keep y as the only variable. Z and x will be treated as if they are just numbers here. So partial f, so in order to say partial f, partial y, can also be written as just f subscript y, like that. So what would be the answer here? The only thing that you have to know here is how do you differentiate hyperbolic trig functions. You know, to say if you have a hyperbolic function, let's say like the way this is shine like that, and then you have maybe f of x inside, and then you need to get the derivative here with respect to x. You know, to say here, first differentiate the argument. So the derivative of the argument will be f prime of x. And then after that, differentiate the trig ratio. The derivative of shine there is just going to be cosh. And then the argument will remain the same. Just like that. Based on that, here, since y is the only variable here, x and z are constants, it means that the derivative of this part here will be 0. Again, I'm starting with differentiating the argument, but the derivative of z will be 0. The derivative of xy, because y is the only variable and it has power 1. So the derivative of y here will just be 1, so that only x will remain. So when I differentiate the argument, only x remains. Next up, differentiate the trig ratio. The derivative of shine there is going to be cosh. So we get that. And then the argument remains the same. So this is what we end up having there as the first partial. So the first part was just to get the partial with respect to y, which we have obtained. And so, yeah, which we have obtained. Second part looks a little bit crazy. But what is happening there and how do we get it? First thing is you trying to understand this expression. Okay, so that is what we have there. So get this as well. Okay, so let's try to expand this operation. It looks like we have to, at first, when I looked at this part here, the z being squared there, my first interpretation was, maybe I'm supposed to take the variable not as z, but z squared as my variable. That was my first interpretation. But I then looked at what is happening on top here. I noticed with the three there, that cube there, doesn't necessarily mean the function raised cube. No, it actually means the third derivative being operated there. So it tells me to say that here you differentiated 3 times. So the first one, the partial derivative of f, and then this first one was differentiated again. And then finally, the third derivative there. So the first one, what do I see? This one here. Z occurs twice. See, I can see x was the last one, but I should have 3 more there. Because I should have perhaps df. You have to get the presentation here. If I have df dx, and I also have df dx here, This is just the same as df dx squared. But a second derivative will be presented as d squared f over dx squared. This is how a second derivative is presented, so that you don't confuse it with a square of a derivative. So in the same way, we understand, so when you just look at the denominator, you might think the z is being squared, but when you observe what is happening on top, you will notice that actually this is a derivative, not an operation being squared. So based on that, we can observe that the first part, it was the partial of f with respect to z. And then seeing that this followed again, it looks like in the second operation, again, it was with respect to z. And then in the third operation, that is when it was operated with respect to x, such that, okay, so I hope that is adding up. So it was this part here that was then combined to give us partial x. So that combined to just give us partial squared f, or the second partial of f, and then this was now partial z. The square now shows up there. And then when put together, now this is how they ended up with the 3 on top, and then partial x, partial z to the power 2. So I hope you've seen how we get to interpret this operation. Very important step. And once you understand how you interpret that, we can then move on to start obtaining what they want us to get. Okay, so what are we seeing? I think I expanded it very well somewhere here. The first thing we want to get is partial f, partial z. So let's get partial f, partial z. So partial f, partial z, everything else is a constant. So I'll differentiate the argument. This whole part will be a constant. X and y, those are just, they're going to be constant this time. So only z will be differentiated. That's negative z. So when I multiply the 2, will give me minus 2 here. And then the power for the z will reduce by 1 to become this power 1. So the derivative of the argument will reduce to that. Now differentiate the hyperbolic trig function there, reducing it to that. The argument will remain the same. Now what follows? Now I want to get to differentiate the same thing I found. I want to differentiate it with respect to z again. In other words, this same thing I've obtained, I now want to differentiate it with respect to z. So I'm now getting the second derivative with respect to z. With respect to z, I now see two functions multiplying. I'll keep minus 2z. Differentiate this part here. When I differentiate this part, what will I get? Differentiate the argument again first, we'll get negative 2z. Differentiate the cosh, we get shine. The argument will remain the same. So here this is by product rule. I kept the negative 2z, differentiated the argument, I differentiated the hyperbolic function. Now I'll keep the hyperbolic function and I'll differentiate the minus 2z. Minus 2z, remember I'm differentiating with respect to z. And I differentiate that, only minus 2 will remain. The minus 2 will make the sign between to be negative. Other than that, the 2 will pop out here. So this becomes the second partial with respect to z. So currently, what I have here, this is the same as partial f partial z. Now I want to differentiate the solution to that. Now I want to do it with respect to x. while this being this. So where's that? I have found this. Now I want to differentiate it with respect to x. So with respect to x, what is happening? So all the other variables will now be constants. Perhaps let me distribute the z in the previous step. This will be negative and negative will be positive here, so I'll have 4z squared. Then we'll have shine here. Then I'll have x, y, minus z, then minus 2 cosh. xy minus z. So this is where we are. So now I want to differentiate this expression with respect to x. Everything else is a constant. Now here we see that there are no complications. This is just one term. This whole lot is going to be treated as a constant because I just said this part here, this will be a constant. So the variable is only x this time. We are going partial x. Only x is a variable. So meaning before I even differentiate, I can start by writing this part so that it doesn't confuse me. So I can have 4z. Remember, these two terms are subtracting, meaning I can focus on differentiating this one minus differentiating this one. So let's start by writing the 4z squared. Now I need to differentiate this part. To differentiate that, we know we first differentiate the argument, what is inside here. What is inside here? Z is a constant this time. Again, in this step, we're doing it with respect to x. So z is a constant. That will be 0 when you differentiate. When you differentiate xy here, the derivative of x will be 1. Only y will remain there. So differentiating the argument, only y survives. Then we differentiate the sign, the shine, and that will be cosh. The argument remains the same. So we're done differentiating the first term. Now I have to differentiate the second term. For the second term again, I don't want to confuse that. I'll start by putting that minus 2 there, because that's just a constant. Now I want to differentiate this expression. To differentiate that, first differentiate the argument. Again, still partial x taking the lead, meaning y and z will be taken as constant. So the derivative of this part will be 0 because that's just a constant. So, and then for x and y, the derivative will remain just y. So y will multiply outside, it will come here. Next, differentiate cosh, that will be shine. The argument will remain the same. So with that, we have differentiated everything. This, of course, well, the operation we're getting is what they want. Partial x, partial z. When you distribute, this is now 4. I just remove the brackets there. Y, z squared. Then you have cosh xy minus z squared. Then minus 2y. Then you have shine there. Z. So this becomes the final solution. Okay, so this is what I got. Any questions there? Do we have any reactions? How did you approach it? What did you get there?